Right, we're carrying on with this dot and cross. Right, distress flares are used to attract attention in an emergency. Right, what we need to do is react magnesium and oxygen. It is an exothermic reaction. Exothermic reaction. Right, so one marker. So exothermic reaction is a reaction that gives off heat to the surroundings. Right, the main things, the main gives off heat. So let's make that a bit bigger. It gives off heat or releases heat. Whatever word you want to use. Right, okay, let's move on. Right, diagram shows the electronic configuration of a magnesium atom. Oxygen atom. So oxygen is that. So we've got, that's called the atomic number, and it stands for the number of protons. Protons are positive particles with a mass of 1 and a charge of +1. This is called the relative atomic mass, and it stands for the number of protons plus neutrons. Right, okay. We need 8. So, okay. The number of protons equals the number of electrons. So we've got 1, 2, 3, 4, 5, 6, 7, 8. That's the... How much do we need? 8. Right, okay. That's got 8. 1, 2, 3, 4, 5, 6. It can't be that. 2, 4, 6, 8, 10. It can't be that. 2, 4, 6, 8. This has also got 8. But now the question is it this one or is it this one? And remember, we said you're only allowed 2 on the first shell. 1, 2. But this has got 1, 2, 3, 4. So it can't be that one. So the correct one is D. So did you see the thinking on that? Yeah, you're only allowed 2 electrons on the first shell. Right, this is a little bit of a typo. Don't worry about that. Right, okay. Magnesium oxide ions. The electronic configuration and charge of a magnesium ion. Remember, an ion is a charged particle. What do we need next? We need to put in a charged particle of an oxide ion. So oxygen we said was 8. So it was 1, 2 on the first shell. Look. And then on the next shell, let's change color for that actually. No, that doesn't help. 1, 2, 3, 4, 5, 6, 7, 8. You've got 1, 2. So we need 2. It will be this one here. So ignore that. Ignore that. So these are your 2 extra. Well, compared to the one that we've drawn there. So it had 8. We've added 2 more. It's got 10. So it's got a full outer shell. It's got a full outer shell. It's got 8 electrons in the outer shell. It's full. So it'll have it's taken on 2 extra minuses, 2 extra electrons. Yeah, so that there is an electron. That is another electron. So it's taken on extra 2 minus. So it's this one here. It's not that, it's not that, and it's not that. Right. So 4 marker. Right, okay. The major use of magnesium oxide is a refractory material, which is a material that can withstand very high temperatures. Explain in terms of its structure and bonding why magnesium oxide has a very high melting point. Right. It has so magnesium oxide has a giant right, because you've got a metal and a non-metal, you get an ionic compound. Yeah, just bear that in mind if you ever forget. Ionic, not combined, compound. Compound. Oh my goodness me, I can't spell anymore. Right, it is a giant ionic compound with many ionic bonds. Right. These consist of strong electro. Let's do that with this. Consist of many strong electrostatic forces of attraction between positive ions and negative ions. Right, you could put Mg2 plus positive ions and negative ions, or 2 minus ions. Right, and then you've got to finish it off by saying these require lots of thermal energy to break. Okay, done. Magnesium oxide is also used as an antacid. It helps relieve indigestion by neutralizing hydrochloric acid. Give the name of the formula. Right. So let's try this here. So you've got magnesium oxide plus hydrochloric acid gives magnesium chloride plus water. No. What will it give? Magnesium chloride. So it will give this. You'll need 2 of them. Right, okay. Now, what I'm going to do is I'm going to look at this bit here. So you go to magnesium chloride. I know magnesium is in group 2, so it produces a 2 plus ion, and chlorine is in group 7, which produces a -1 ion. Right. I'm not interested in the sign. If I can delete the sign. Yeah, and the sign, I'm just going to put 1 there instead. New 1. Now, because these two are not the same size, I'm going to cross over. So really what I've got MG1CL2, but I do not need to write this one. So it's MGCL2, so I really need to put a 2 here. Now, if I check these out, this is what I've got. So the salt produced is magnesium chloride. Let me write it so then you can read it. And the formula is MgCl2. It's not MgCl, it's not Mg2Cl, it's MgCl2. And this is the reason it was this. I think I've seen it called the crossover method. Okay, let's keep going. Right. You've got giant covalent, giant ionic, giant metallic, and simple molecular. Right, what we've got here is substance A, the electrical conductivity. When it's a solid, it's poor. When it's a liquid, it's poor. And it's got a... So that tells you straight away it's covalent. Right, I know it's going to be covalent. Now, it can be either that or that. Now, the thing is, because it's got a low melting point, it's going to be simple molecular and covalent. And the only option they've got that is there. So we don't need the word covalent in there now. Right. Again, you've got poor electrical conductivity when it's a solid and when it's molten or liquid, but it's got a high melting point. So you know it's covalent, and the only other covalent one is giant covalent. Now, I know for a fact metals are good conductors of electricity. That's poor when it's solid. So it's going to be this. It's good when it's electrical, when it's solid, and when it's molten or liquid. And it's got a high melting point. So it's going to be, well, we'll have to put giant metallic. And finally, that will be giant ionic. Right, let's keep moving on. You have magnesium, okay. So we've seen magnesium chloride before. There's the magnesium atom, so we're looking at the electronic configuration. So if I had to do this as a number, I would say 2 dot, because you've got 2 on the first, you've got 8 dot, and then you've got 1, because you've got 8 on the, let's take this, you've got 1, 2 on the first one, you've got 1, 2, go around 3, 4, go around 5, 6, go around 7, 8. So you've got 8 on the next one, and then finally on the outside shell you've got 1 and 2. That's it. So it'll be 2, 8, 2. For chlorine, it'll be 2.8.7. Why 7? Because you've got 7 on the outside shell. 1, 2, 3, 4, 5, 6, and 7. Right. It's a 3 marker. Describe how magnesium atoms and chlorine atoms form magnesium ions and chloride ions. So what's going to happen is this. One of these will go here to give it a full outer shell. You've got another chlorine. atom here. Just say here, right? And this one is going to go there. So we can say the magnesium atom loses 2 electrons to become Mg2 plus ion. Each chlorine atom gains an electron to become Cl minus ions. So it's going from magnesium to chlorine. Right. Draw a diagram to represent the electronic configurations of each of the ions of magnesium chloride. So what you do, because it's an ion, you're going to have a square bracket. So if we label that up Mg, our first shell has got 1, 2. Our next one's got 1, 2, 3, 4, 5, 6, 7, 8. So what's happened is it's lost the outer shell. Now we're going to do the same thing with this one. Right, so we've got Cl. We've got 1. Right, and then it had 1, 2, 3, 4, 5, 6, 7. And what's happened is that one there, so let's use the same color. The electrons, the 2 outer electrons that were on the outside shell, one of them is going to come up here. So there you go. That's what you're going to have to do. Right, we need to do a dot and cross diagram for carbon. So and they only want you to use the outer electrons, otherwise it becomes too messy. What I'm going to do is I'm going to focus on carbon. I know carbon is 6, so I'm looking for 6 electrons. I know there's 2 on the inner shell, we don't need those, and I need to put 4 on the outer shell. So I'll say, let's do it this way so it makes it easier. 1, 2, 3, 4. And now you've got the electrons on oxygen. So oxygen is, we need 8. So we've got 2 on the inside. We need 6 on the outside. So look, we need 1, 2, 3, 4, 5. No, let me do it this way. 5. I'll transfer those in a second. 6. 1, 2, 3, 4, 5, 6. Now what's going to happen is, let me get this. This electron is going to come here and they're going to share it. This electron is going to come here and it's going to share it. So now, same thing that's going to happen to that. That's going to come over here and share it. And this is going to come over here and share it. So now what you've got, now watch this. You've got, look, for this one, you've got, this is the outer shell. It's an amazing shell. You've now got, let me get this right, 1, 2, 3, 4, 5, 6, 7, 8 electrons for oxygen. That's happy. The same thing happens on the other side. So what I can do is just get rid of them. Now we look at carbon. So if you look at carbon's outer shell, it looks like this, and it's got 8. 1, 2. Let me get this. 1, 2, 3, 4, 5, 6, 7, 8. So it's got 8 electrons, so they're both happy. So this is the electronic configuration for carbon dioxide. Right. Indium is a metal. Describe the structure and bonding in a metal. So what we can say is that we're not interested in what's holding it together. Right, we're just interested in its structure. That's weird, that is, but okay, that's what they've said. So you can say that indium has layers of ions and a sea of delocalized electrons. That's the structure. Right, I would put here positive ions just to make it exact. Ions is too vague. So you've got indium has a layer of positive ions and a sea of delocalized electrons in a, you can say, lattice or giant lattice structure. There you go. And what's holding it all together is the electrostatic forces of attraction. And what's holding it together? The bonding. There are, just put all this in, it doesn't matter. There are strong electrostatic forces of attraction. Between what? Between positive ions and a sea of delocalized electrons. Okay. Why is indium malleable? Why is indium malleable? That's a good question. Right, malleable means it can be bashed into or squashed into sheets, like your car bodies or panels, or right. Ductile means it can be drawn into wires. You can pull them into wires. Why is it malleable? And the answer is the same for both, because the layers of ions can slide past each other when a force is applied. See if you can learn that word for word. That'd be good. That. Okay, we'll just trying to figure out whether to do that. Okay, what we'll do is we'll get this done form another video. So 5-1. We need to complete the table. Ammonia, I know, is, remember we said, look, ammonia is a molecule NH3, 1 nitrogen, 3 hydrogens. Ammonium is an ion, it's NH4 plus. Very important. This comes up a lot. Just learn it. Ammonia is a compound and it is a covalent compound. I know that. Hydrogen chloride is a compound and it is a covalent. I mean, how do I know that? Non-metal, non-metal. Non-metal, non-metal. So for ammonia, it's NH3, they're both non-metals. H, N, yeah, okay. Oxygen, right, it's an element. Element. And it runs around in pairs. So remember what we said, so it's covalent, yeah. We know it's called a diatomic. Magnesium oxide, metal, non-metal, that makes it ionic. Metal, magnesium, oxygen, non-metal, and it's going to be a compound. Let's keep moving on. So what did we say magnesium oxide was? We know magnesium and oxygen. So we know that's a 2 plus because it's in group 2, and that gives a 2 minus. And because this, right, I'm not interested in the signs at the moment. I know they're both the same size. So if you look, they're both the same size. Because they're both the same size, I can rub them off, so it'll be MgO. It will be MgO, which is MgO. That one. Right. Which state symbol represents a physical state of hydrogen chloride at room temperature? Hydrogen chloride at room temperature is a gas. I didn't know that, but it is a gas. So hydrogen chloride at room temperature. Yes, hydrogen chloride. Yes, and then when you look, hydrogen chloride, hydrogen and chlorine at room temperature is a gas. And then when you put it into water, it becomes aqueous. Yeah, aqueous. And we know that as what? Hydrochloric acid. There you go. Right, we'll call it quits there because it's almost half an hour and then we'll move on to the next one.